Okay, so welcome to the final session for today. And in this session, we have two talks. The first one will be given by Sandipan Manna from ICTS-Pune, and he's going to tell us about projected ensemble in a system with conserved charges with local support. Yeah, over to you.
Thanks for the introduction. And also I thank the organizers for this opportunity. So I will talk on projected ensemble in a system with conserved charges with local support. I will explain the terms as we go along. This work was done in collaboration with Cedric from ICTS Bengaluru and Cedric from ICTS Pune, my supervisor. And this is recently posted on archive. Okay, so this is the outline of the talk. So first we will talk about what is a quantum state ensemble and how it can be considered as an unraveling of density matrix. And then we'll briefly discuss what is distribution of states in Hilbert space and how projected ensemble generally emerges from it. We'll talk about LB Hamiltonian that we have studied in this particular problem. And then we'll talk about probability distribution of output bit strings, so which is an important part of this work. And finally, we'll go to projected ensemble constructed with an LB Hamiltonian and we'll present some numerical evidence. Okay, so what is an ensemble of quantum states? So, okay, it can be just thought of a collection of pure quantum states, or you can think it of a black box which generates a certain number of states on demand. And those states need not all be unique. Some of the states might be repeated, like, like here, psi2 and psi2, they're coming twice. So some of the states might be repeated, but it is a machine that generates n number of states on demand with a certain probability distributions. Once you have these states, these pure states, you can calculate any observable in your lab. You can just do a projective measurement on it, using any observable. You will get an eigenstate of those observable after each projective measurement. And finally, you can take the mean value of all those outcomes. You'll get the expectation value of that particular operator. So that is just simply conventional density matrix. Don't, okay, rho one just means the density matrix. Okay, yeah. So then the natural question emerges that, okay, we have a quantum state ensemble, which is just a collection of quantum states, and we have an associated density matrix that somehow labels it. But is it unique? Turns out no. There might be many unraveling for a particular density matrix. This is just a simple example. So you can have two different state ensemble. One generates state 0 with 50% probability and state 1 with 50% probability. And you have another ensemble which generates coherent states, plus and minus with equal probability. Both of them has same density matrix. So if you calculate expectation value of any observable, they will come out to be same for both of these ensembles. In this case, it is 0 if you calculate sigma x. But clearly these two ensembles are not same. But how can we distinguish them? Okay. Turns out that if we can somehow keep track of expectation value on these individual components of this ensemble, so the ensemble generates a chain of pure quantum states. So if you calculate the expectation value of certain operator on each of these quantum states and draw the probability distribution of it, then they differ. So for the first ensemble, you see that whenever you measure sigma x, it will always come out to be 0. But for the second ensemble, 50% of time you will get expectation value 1, and for 50% of the states, it will come out to be -1. Now this distribution is captured in the moments of the ensemble, quantum state ensemble. Yeah. So this is just an illustration. So we already saw the density matrix is same for both of these ensembles. But if you just look at the second moment, which you can just think of some sort of correlation matrix between the elements in the quantum state vector, they clearly differ. And this second moment of ensemble actually captures second moment of any observable that you can calculate. For example, second moment of any observable is actually related with the variance of those observables, and it also measures the fluctuation. Okay, so till now we saw that density matrix does not uniquely represent a particular quantum state ensemble. There might be many ensembles for a given density matrix, and just calculating expectation value cannot distinguish between different ensembles with the same density, with the same density matrix. But higher moments of any observable can distinguish between different ensembles. So the conventional study on fate of isolated quantum systems has generally focused on expectation value. So what normally is done is that you look at a pure state, time equal fit with a chaotic Hamiltonian for thermalization study, and then looked at the reduced density matrix of the subsystem. There, ETH predicts what the reduced density matrix would look like and what should be the equilibrium value of the expectation values. But can we, okay. So this is our reduced density matrix, but we already saw that given the reduced density matrix, there might be many state ensembles which are consistent with that density matrix. Then we can ask, okay, can we say something about this, the quantum state ensemble itself in the context of thermalization? It turns out that there is no unique ensemble. So how can we associate a particular ensemble with this density matrix? So it turns out that there is a natural protocol that is called projected ensemble, which can actually associate a quantum state ensemble with a given reduced density matrix. Yeah, so this is the protocol that you use to construct the projected ensemble. You have a pure state, psi. Then you divide the system into two parts, A and B, and then do projective measurement on one of the subpartition. So this is the B. And once you do a projective measurement on any basis, you can choose any complete basis. You get a pure state on A, conditional on the outcome in B. So after post measurement, this is your entire state. So this is a pure state in A, conditional on the bit string that you get in B, and this is a bit string in B. You can collect all these states and also keep the label that all these pure states are labeled by the measurement outcome in B. Yeah, you can collect all the states and make an ensemble out of them. And all these different pure states will be distributed according to certain probability distribution. And what is this probability distribution? It is just the expression value of projector on individual bit strings in B. If you want to think it in terms of trajectory, then you can think that, okay, I have a pure state, and I can take a snapshot of all possible trajectories post-measurement, and then create an ensemble out of them. So this is an ensemble of pure states, where states are labeled by the measurement outcome in B. Okay, how to do it operationally? You just take many copies of the full state, that is psi AB, and keep doing projective measurement, and don't discard the outcome in B. Keep the bit strings and also the pure state that you get in A. Finally, you can tabulate them, and you can find out what is the probability of getting individual psi A. And this is accessible in modern quantum simulators using some techniques like fluorescence measurement. And if you just take the mean of all these conditional states, you will just get the reduced density matrix. But in that case, you're actually discarding the information regarding the path. So B can be considered as a path. But we will keep the information regarding the path. So all the pure states in A are labeled by the path in like measurement outcome information in B. Okay, so till now we saw that projected ensemble is a protocol that can generate a quantum state ensemble given a pure state. The pure state can be anything. It can be an eigenstate, or it can be a time-equal state under a chaotic Hamiltonian, or any Hamiltonian you like. ETH, which is the conditional statement regarding the thermalization, describes the local expectation value of any observable. It predicts that the system goes to this ensemble, which is determined by the conserved charges of the system. Generically, for chaotic system, it is just energy. Projected ensemble is a natural protocol that lets us associate an ensemble with the reduced density matrix that we get. Now the question is whether it has any universal feature. Okay. First, we will look at the chaotic system with effective infinite temperature. Effective infinite temperature actually means that the beta, which is related to the energy expectation value, is 0. For such system, if we construct the projected ensemble, it goes to a hard ensemble, which is just a uniform distribution of quantum states on the Hilbert space. It has certain properties, which is it is an unitary invariant measure, and also it is a maximum entropy ensemble in the Hilbert space. If you want to see a single qubit example, this is a single qubit Dhar distribution on the block sphere. Okay, but from this block sphere picture, you can easily see that this will always give you the maximally mixed identity density matrix. So any expectation value that you calculate will be 0. But what happens if your system has some finite temperature or some finite conserved charges? Then the density matrix is not identity. It is something like a generalized Gibbs ensemble. It is like e to the power minus lambda q. In that case, you have a density matrix which is not identity. And as we discussed earlier, that or a given density matrix rho 1, you can have many, many ensembles. Now, which one is the natural expectation would be that the quantum state ensemble that you are getting will be maximum entropy. But which one out of them is maximum entropy? That is given by the Scrooge ensemble. So you take your reduced density matrix, construct all possible unraveling of it, all possible ensembles out of the reduced density matrix, and then ask which one have minimum accessible information, which is equivalent to asking which one has maximum entropy. That turns out to be Scrooge ensemble, and it is constructed as follows. Here, it is given here. So you just sample states from her ensemble, distort them with your reduced density matrix, and collect them with the probability given by this. Okay. Yeah. This is just a comparison. So the first case is the Haar ensemble for a single qubit. This actually represents the identity density matrix, and expectation value of any operator will be 0. And this is a Scrooge ensemble for a single qubit where expectation value is minus 0.95. You see that most of the states are concentrated near the one state. Okay. Now, here I talked about measurement. This alpha is actually referring to what is your measurement basis. It's not necessarily a computational basis measurement. It can be any basis, any complete basis. Yeah. So now first we'll briefly discuss what happens for a system with global equal symmetry. That is like an XXC model, where you have total sigma j equals some constant, which is conserved under dynamics. For such system, if you measure a partition B, it reveals the charge about B, total charge in B. That immediately restricts what can be the total charge in A, because total charge is conserved. So the possible states, conditional states that you can get in A are constrained. They cannot be any state. They has to satisfy this rule that the charge has to be QA. It is known that for such systems, the projected ensemble converges to a mixture of multiple Scrooge ensemble. On the other hand, if you measure in some charge non-revealing basis, then it approaches to a single Scrooge ensemble. What do I mean by charge revealing and charge non-revealing measurement? So if your conserved charge is sum over sigma g, then charge revealing measurement is measuring in the z basis. On the other hand, if your conserved charge is also sigma g, and if you measure in sigma x basis, then measurement doesn't reveal anything about the charges of the B part subpartition. That is a charge non-revealing measurement. Not much is known between these two limits. So yeah, how does it go from charge revealing to charge non-revealing, and how the nature of projected ensemble changes? Okay, so we are studying a L-bit model. It is given by this. So it is a long-range interacting model where the interaction strength decays exponentially with the distance. This is your some sort of length scale that you can use to moderate your interaction length. These are random numbers, Uij. These are sampled from random distribution. And this particular model may look like a classical model, but this is not. Entanglement grows under this particular dynamics. And these are quantum operators. And your state is not a classical state, it's a quantum state. The conserved charges of this particular model are strictly one local. So sigma g's are the conserved charges. And under dynamics, the occupation of two levels does not change. So it conserves the occupation of 0 and 1 level. We'll start with the initial state, which is a random product state, where theta are chosen from hard distribution. Like theta chosen such that your single qubit states are hard random. For such a state, the density matrix will be a diagonal density matrix. And our measurement basis is labeled as 0 and 1, but these are not computational basis. Okay. Our computational basis will be labeled as up and down in z direction. And we can choose any measurement direction, and those will be marked as 0 and 1. They are related to computational basis to this relation. So just to recap, we are taking an initial state, which is a random direct product state, evolving it with the L-bit model, which has strictly one local conserved charges. That means it actually conserves the occupancy of both 0 and 1 level. And finally, construct a projector ensemble by doing a partial measurement on the B subpartition and collecting the pure states in A. And this projective measurement is given, it's done in a generic measurement basis, not necessarily in the computational basis. And this measurement basis is labeled by alpha. Okay. First, we can look at how does the elements in the projector ensemble evolve with time. So here we are showing the second moment for two cases. In one case, your A system has 1 qubit, and in other case, it has 2 qubit. And different colors denote different system size, total system size. And you see that at long time, the fluctuation becomes very small at large system limit. So we can actually consider time averaged quantities at large time limit. And to get the time averaged quantities, we consider temporal ensemble, which is nothing but collecting time equal states at a long time interval. So just take a large time, tau1 equal to maybe 10 to the power 3, and tau2 equal 10 to the power 4, and collect time equal states in this interval. So we're implementing time averaging through averaging over this temporal ensemble. Okay. So this is an important point, distribution of probability of bit strings, probabilities of bit strings. So what is this thing actually? So given a state, psi, a pure state, you can do projective measurement on any basis, the basis that we already shown before, a complete basis. You'll get a bit string output. And for an n-side system, there will be 2 to the power n possible bit strings. You calculate all these probabilities, probability of getting each individual bit strings, and then plot them, make a histogram out of them. And this is that histogram. It is in semi-log plot. It is in a semi-log plot. It turns out that this distribution follows a Proto-Thomas distribution, which is nothing just an exponential distribution with a mean mu. This mu does depend on the measurement basis and the initial state that you choose. Okay, so we have shown the data here for 3 different angles: 0.5 pi, which is x-axis, which is measurement in the x basis, and 0.25 and 0.125. 0 would mean measurement in the z basis. So you see that for 0.5, distribution matches Proto-Thomas distribution very well. And for 0.125, which is closer to z basis measurement, there is a deviation at even short p values, small p values. This part actually affects the distribution most. So for measurement angles closer to x-axis, the agreement with PT distribution is very good. As you go away from x-axis measurement and go closer to z-axis measurement, the agreement becomes worse. Okay, so this was the distribution in a temporal ensemble. So temporal ensemble is collection of time equal states. You take all those states, measure measure the probability of getting a particular bit string for all those time equal state and histogram them. Then you get this plot. These are for 2 different bit string. And this is equivalent to just calculating the expectation value of projector on this particular bit string. Okay, so the last plot was regarding the temporal ensemble. This is for a single time-equal state. And you calculate the expectation value of all possible bit string projector. So it is just this. So you take all possible B, calculate PB, take a single state, psi, which is a time-equal state at a very late time, and histogram them. This is the histogram that we get for 2 different measurement angles, 0.5 pi and 0.25 pi. Okay. So for x-axis measurement, you see here again we see exact Proto-Thomas distribution. But for measurement at other angle, pi by 4, this is not a Proto-Thomas distribution, but this is sum of multiple Proto-Thomas distribution, properly normalized. But Proto-Thomas distribution occurs at bit string level in both cases. Okay. So these are the principal finding that Proto-Thomas distribution occurs in temporal ensemble for measurement angles which are away from z-axis measurement. And for a single late time evolved state, Poisson distribution exactly emerges for alpha equal 0.55 with a mean 1/2 triple L. And for other angle measurement, we get a sum over multiple Poisson distributions. Okay. Once we have this data, we can actually, once we have this observation, we can actually show that for the L-bit model, for any measurement angle away from 0, at thermodynamic limit, it goes to Scrooge ensemble. I will not show the proof here, but I will show some numerical evidence. This is how the trace distance from Scrooge, this is distance, we are actually calculating trace distance from the second moment of Scrooge ensemble and projector ensemble. You can see that these different colors actually mean different system size. This is the data for where the A system size is 2 and the BART system size. Total system size is L. These are different colors denoting different L. For both measurement angle 0.5 and 0.125 pi, the trace distance saturates to a finite value at long time. And this finite value actually goes down with increasing system size. The decay with time follows a polynomial. And this is an exponential decay with system size. So you can expect that at thermodynamic limit, both these angles will cause projector ensemble constructed through the measurement with both these angles will cause it to converge to the Scrooge ensemble. And this is the scaling with system size. So you say if your measurement angle is below or above 0.2 pi, you see a clear exponential decay with system size. This is the slope. But as your measurement angle goes closer to 0, that is z-axis measurement, the decay, it does not decay any further with system size. So it says that this one does not go to the Scrooge ensemble, at least not the Scrooge ensemble that we are comparing with. Yeah. So the main output is that we observe convergence to the Scrooge ensemble for the projector ensemble constructed with L-bit Hamiltonian whenever we measure in any angle apart from 0. At least larger than 0.2 pi. Okay. I will conclude here. So the main result is that for L-bit model, the projector ensemble is described by an universal ensemble, which is Scrooge ensemble, for any measurement angle apart from 0 at thermodynamic limit. Emergence of projector ensemble, emergence of Poisson distribution in bit string in output bit string distribution is actually can be related to the emergence of Scrooge ensemble. There are additional results regarding the system size dependence and semi-analytical proof, and also we studied the Floquet MBL model, where also we see similar trend like this. Those are described in this archive. Thank you.
Okay, let's thank Sandipan for this wonderful talk. Are there any questions?
So you talk about the Scrooge ensemble.
Yeah.
So, but you cited the work by Goldstein and Tumulka and Leibowitz. So it's the same thing as the gap measures they introduce? Or because you take the reference as the R measure on your state, they take a Gaussian one, but is it the same thing at the end?
Sorry. Asking about this, but right? So,
yeah, this one. It should be the same as a gap measure in of Goldstein, Tumulka, and Leibowitz.
Yeah. So given that you have this fast moment is slow in that case.
Okay.
Yeah.
Thank you.
First of all, maybe I missed what is D here?
Oh, it is a sort of, you can think of, this is called accessible information, but you can think it of as some sort of measure of entropy. Or
What
D,
is the
or
D?
D is just a Hilbert-Swiss dimension.
Oh, I thought it's a operator. Also, when you measure, you measure in a with just alpha, but there, like, is there a symmetry why you don't use other angle of the, like, it does not, it is not the whole block sphere space?
We are looking at alpha between 0 to pi by 2. Right?
0 to pi, well, then,
It will again repeat. So if you go to pi by 2 to pi,
no. So I'm saying there can be e to the power I alpha as well. There can be a phase in the measurement. When you're doing measurement, you are choosing particular alpha.
yeah.
There can be as well beta where there's a phase. Is there a particular reason?
Oh, okay. Here?
Yes, in the measurement basis, cos alpha by 2 plus
It will not affect the results in this case because we are, the measurement outcomes will not depend on this phi, the probability of getting individual bit strings. That will not depend on phi.
the probability will not depend on the
Yeah,
phase.
the probability of getting individual bit strings, this PB, this quantity will not depend on phi once you do the sampling.
Is this because of like what is the reason? Also, is there a particular role of the three body operator like 3 sigma z?
No. You can, in principle, there are higher order terms. We have truncated it at three body.
So if I just take one and first and the second term, the result.
That will change the time scale. So this convergence time scale.
Thank you.
But even first and second order terms should work.
Thank
I
you.
expect that convergence time scale will be longer. Just keep.
Since there are no further questions, let's thank Sandipan again.
Thank you.